Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing Linear Algebra 1. This is Chapter 5, Linear Transformations. Section 5.3 is going to be linear operators on the plane R2. So we're going to give a giant demographic, which is essentially what we're going to do this lecture. Do a demographic of all the different types of linear operators moving points around in R2. Let's get to it. We're going to do a very large number of linear operators in R2, but before we do that, let's remind ourselves that a linear transformation from the same space to the same space, in this case R2, is called an operator on R2, and hence moves points around. T is going to be linear, remember, if it spits out scalars and splits sums. So we have these two nice properties. And finally, if we do have that T is a linear operator, then we're going to have any basis completely determines where all vectors go under that linear transformation, because I can write any vector in R2 as a linear combination uniquely as those two vectors because they're a basis. I get this unique linear combination, and therefore T of X is T of this guy, and I can spit out scalars and split sums, so I get this nice property that I can completely determine where every point in R2 goes by knowing where the basis vectors go. And in particular, we know where to get the standard matrix from the images under the canonical basis, I and J in this case. This is essentially what we'll do in many cases, and we'll find the standard matrix of the operator immediately and view it as a matrix transformation. And we saw before in the previous video that all matrix transformations are linear transformations. So this will give us a good picture of the basic types of useful operators on the plane. Let's do that. All right, I'm plus a cat, but the first category sort of we'll do, and then we'll do another video after this sometime, and we'll do the most generic, difficult versions of all of these. But for now, as an intro, I'll just give you the three easy ones as he attacks my head. So we're going to do reflections first, and the relatively easy categories are going to be reflection about the x1 axis, the x2 axis, and the line x1 equals x2. Again, in another video, we'll do reflections about a generic line in the plane. But for now, let's do these three categories and see why they're linear and what their standard matrix is, and then go on to our next category. Okay, you go. I'll do these. So first of all, the idea here is just geometrically what we're going to do. Kitty, you gotta stop messing with all the props in the background. I gotta pick you up again. I know you're very big. So what we're gonna do is we're gonna look at the starting vector as a point in the plane, and then we're gonna move the point around. And in this case, we're gonna see where it goes, and then we can get an idea of what the linear transformation is and what the standard matrix is. So this is in fact T of X. And in this case, this is also T of X, our image when we start with a vector X or a point X, and this one also is T of X. What we want to do with that is find an explicit expression for the standard matrix in each case, and therefore it's a matrix operator. He's messing with everything. Reflections are linear. What we're going to get is this says that T of x1, x2 moves to the point. The x1 coordinate stays the same, but the x2 coordinate goes from its positive to its negative across the x1 axis. So that goes to x1 negative x2. And if I want to view that as a 2 by 2, all of them are going to be 2 by 2 matrices because they're operators on R2 to R2. So this will be an A 2 by 2 matrix. So this is going to give us what? I want to view that as x1, x2. And what is that going to be? I need a positive x1, no x2s in the first coordinate. And then I need a negative x2. So I'm going to get 0, negative 1. So because this is a matrix, this is a linear operator on the plane, and this is a standard matrix. The standard matrix of T is going to be 1, 0, 0, negative 1. For the next reflection, what we're going to see is same thing. I want to look at this T of general vector, x1, x2, is going to go to this time the x1, or the x2 coordinate stays the same. The vertical stays the same height, but the x coordinate goes to its negative, so this will be negative x1, x2 this time. which is, of course, a 2 by 2 matrix multiplied by x1, x2, which is going to be what? This time I need negative 1, 0, 0, 1. So this is the standard matrix of t in this case for reflections about the x2 axis. This is going to be negative 1, 0, 0, 1. A nice diagonal matrix again. And finally, for this one, I didn't squeeze it in there, but if I have x1, x2, where does this go? It flips the coordinates. This is again how we deal with the graph of a function of one variable. The graph of its inverse is the reflection about the line y equals x, because it changes the a to b to b to a. So it interchanges the coordinates, it flips them. So what is t of x1, x2 this time? This is equal to x2, x1, which is equal to a 2 by 2 matrix times x1, x2. I'll have to squeeze it in there with the standard matrix of t. This is going to be, oh, that became a weird bracket. This is going to be what? I have to flip them, so this should be 0, 1, 1, 0, and that will give me x2 in the first coordinate and x1 in the last coordinate. So the standard matrix about, or reflections of the line y equals x or x2 equals x1 is going to be this matrix. Let's do the next category. All right, for our next two categories, we'll do orthogonal projections onto the x1 and x2 axis. Again, we can do this onto a general vector in the plane if you want, or in a vector in the direction of a line, but we'll do that next time in the more complicated general linear operators on R2. The first one is projection onto the x1 axis, and again, we can just do this intuitively and pictorially. What we're going to have is an arbitrary point x1, x2, and we want to push it onto, regardless of which quadrant it is in, we want to push it onto the x1 plane. What that's doing is, whatever the x2 coordinate was, we're now making that x2 coordinate 0. So the image of the vector under t will be x1, 0. What that tells us is t of x1, x2 is going to be x1, 0, which will be a 2 by 2 matrix times x1, x2, which is going to be what? We want an x1 in the first one, and then we want nothing. So we're going to get this nice matrix. Standard matrix of t for projection onto the x1 axis has 3 zeros, and it kills a bunch. So those are the ones you want on an exam, so that it kills a bunch of the coordinates, and the matrix multiplication when we do composition won't be so bad. Let's do the next one. What is t? T of x1, x2. You don't have to put the curly brackets if you want to be lazy. I'm just being lazy. Hitting a point with t gives me, in this case, it kills, if we look at where it's going to go from x1, x2, and this time it's going to kill the x1 coordinate. So this is going to go to 0, x2, regardless of the vector we pick. And that is going to be a 2 by 2 matrix multiplied by x1, x2. And what is that going to be? This time I want no x1s and I want an x2. So I get this matrix, which will be essentially a linear operator in both cases, because we have a standard matrix in this. So this is a matrix operator. T in this case is going to be 0, 0, 0, 1. So those are the orthogonal projections onto the x1 and x2 axis, and they are linear operators. Let's do a few more. All right, for the next one's contraction and dilation, I'll do contraction essentially growing in one direction or growing in the other direction, or growing in both directions, whether it's the same or different scalars. If you're between 0 and 1, you're going to contract. If your k is larger than 1, you're going to dilate. But in either case, what we're going to get is when you want to dilate or contract in one direction or the other, we're going to do specific linear operators. Or if I want to do it, contract the entire plane, whether it's in the contracting is the same in both directions or different, we're going to use these types of linear transformations. What are they specifically, and what are the standard matrices? In this case, again from the picture, I have this point x1, x2, I'm moving it to, I'm scaling, and in this case growing the x1 direction or shrinking the x1 direction, but I'm leaving the x2 direction alone. So this says t of x is going to be equal to x1, x2 always. It's going to be k1, x1, x2, which is equal to a 2 by 2 matrix times x1, x2, which is going to give me what? This time I want k1 times x1, 0, and then 0, 1. So my standard matrix in this case is going to be the standard matrix, this one, K1, 0, 0, 1. You don't have to have the index. I just did this because we're in the x1 direction. Same thing for the x2 direction now. T of x, which is x1, x2, is going to be x1, K2, x2 this time, which is going to be a 2 by 2 matrix multiplied by x1, x2, which is this time what? I'm going to want identity in the x1 direction and scaling by x2 in the x2 direction. So this will be dilation contraction in the x2 direction, in the vertical direction. And then how do I do this here? What's the standard matrix? Here we're going to get 1, 0, 0, K2. And here finally we're going to get T of x is equal to what? We're going to get K1, x1, K2, x2, possibly different. They're the same, you just get a nice diagonal matrix multiplied by the identity. But in this case, we're going to get a 2 by 2 matrix multiplied by x1, x2, which is going to be what? K1, 0, 0, K2. And if those guys are equal, you get a diagonal matrix. Well, this is a diagonal matrix. You get, if K1 equals a K2, you get a multiple of the identity matrix, is what I mean. So in either case, T is equal to K1, 0, 0, K2. This is dilation and contraction in the plane. Let's do a couple more categories. All right, let's do shear in the x1 and x2 direction. Shear force is like pushing on a building or something with wind or something like this. And what we end up getting is we're going to move the x1 direction, not a multiple of the x1 direction, but it's going to be x1 direction plus a multiple of the x2 coordinate. And so long story short, I'll give you the standard matrices of these, and therefore it's a matrix operator and therefore a linear operator. So in this case, T of x1, x2 is going to be what? It's going to be this x1 plus kx2, and then the x2 direction didn't move. Again, this is going to be a 2 by 2 matrix times x1, x2, moving points in the plane around. What do I get? In this case, I need a 1 and a k, 0 and 1. So this is shear force in the plane in the x1 direction. This means that the standard matrix of this linear operator is 1, k, 0, 1. Same thing for the x2 direction. In this case, T of x1, x2 is moving the points, so I'm going to get x1 stays the same, and then x2 plus a multiple of x1, which is going to be a 2 by 2 matrix again times x1, x2. What is that matrix? Again, in this case, I want to leave x1 alone, so I'm going to get 1, 0, and then I want a k and a 1 so that I can get this row here. What does that mean? The standard matrix of shear force in the x2 direction is equal to 1, 0, k, 1. Let's do one more category and then I'll be done with the video. We might do an example at least, and we'll do some composition to remind you of the composition from the last video. So a couple more scenes. Let's do one more type. Number 11 we'll leave on a prime number. Rotations in the plane. All right, with the last one we're going to do in this video anyways, let's do rotation counterclockwise through angle theta in the plane in radians, not degrees, radians. So what are we going to do? This time I'm cleverly going to use the fact that 1, 0 and 0, 1, or I and J are a canonical basis, the E1 and E2 of R2, and we know that we can get the standard matrix of linear transformation by looking at the images of the canonical basis of R2. Therefore, I'm just going to look at this and find the standard matrix this way. Cleverly, if I take the vector 1, 0, and I rotate it through counterclockwise through an angle theta, say, then I'm going to get the fact that where do we stop? The image point, which is T of x, in this case, or let's call it R theta of x for rotations. And this one, of course, is over here. I just want to know what's happening. R theta of x is equal to, this is what's happening this wasn't of x now. I have to be careful. This was of 0, 1, and this one was of 1, 0. Where do those go? When I look at those images, what I find is that R theta of 1, 0 is equal to the vector cos theta sine theta, and r theta of 0, 1, the other vector, is going to be negative sine theta. I find using geometry, this is in the second quadrant, so negative sine theta, and then cos theta again. So we get cos theta. And what does that give us? This says that the standard matrix of rotation through counterclockwise through angle theta in the plane is equal to r theta of E1 column r, take it easy, r theta of E2, which is these two guys, which says that the standard matrix of rotation counterclockwise through angle theta is equal to cos theta negative sine theta sine theta cos theta. I always wanted to point out a whole bunch of things, but let's get to it quickly. If I look at the determinant of this thing, I see that it's invertible, so it has an inverse matrix. The determinant is cos theta times cos theta minus minus, so plus. So cos squared plus sine squared is always 1. So the determinant is 1, which is not 0. The inverse is going to be cos cos sine negative sine, which if you put negative theta in there, you will get the same thing, which says that this is an invertible linear transformation, and the inverse is just going clockwise, going the other direction through the same angle. The rotation matrix is definitely a linear transformation of the plane. Now the idea is, on exams and assignments, I give you a whole bunch of the demographic of the rotations in the plane, or what's the next video, rotations in, or a demographic of linear operators of the space, not just space, the space, the one we're in. And then what we're going to do is expect you to, I'll say, do this rotation through 30 degrees counterclockwise, and then do a projection, and then do a reflection, and tell me what the standard matrix of that is. And what we mean by that is find the composition of all of those matrices, and we do that by multiplying on the left by all the standard matrices. Let's do an example of that, and then we're out of here. Okay, to finish up, what we're going to do is example, find the standard matrix of the transformation on R2 obtained by first reflecting about the line x2 equals x1, then dilating in the x2 direction by a factor of k equals 2, and then finally rotating counterclockwise through pi over 3 radians. So I want to do 3 things. The idea is find the standard matrix of each one, and then find the composition by multiplying on the left by each of the successive matrices, first to last. Let's do that. So what's the solution? The solution is for the first operator, let's call it T1. We have reflection about that, so the standard matrix of that is going to be 0, 1, 1, 0. I'm just memorizing from my demographic this time. The standard matrix of T2 is what? Dilation in the x2 direction by 2. So that's going to say we're going to leave the x1 direction alone, and we're going to multiply by 2. Now you can see all the horrible coefficients are gone, and we just have constant matrices. We're going to multiply those together. And then what's the last one? Rotation, or T3 if you want to call it, but rotation through pi over 3 radians. The standard matrix of that is going to be cos of pi over 3 negative sine of pi over 3 sine of pi over 3 and cos of pi over 3. So then yes, what is cos of pi over 3 and sine of pi over 3? Cos of pi over 3 is 1/2, that's correct. So this would be negative root 3 over 2, root 3 over 2, 1/2. Now I have 3 matrices, and now you have to multiply this root 3, but let's do the first ones first. So what does this say? This says that the standard matrix of R pi over 3 following T2 following T1 is equal to, this is why I read it in the following scenario, so then you remember this should be the standard matrix R pi over 3 times T2 times the standard matrix of T1, which is going to be equal to, let's squeeze it in there, 1/2 negative root 3 over 2 root 3 over 2 1/2 times T2 1 0 0 2, which is a diagonal matrix, which is 0 1 1 0. What's going to happen to that? That's equal to, and now here's where I use the rule and no one even cares. One of the nice properties that we have is association of multiplications. One of the nice properties of matrices, which makes it a ring eventually, is association. So what I don't want to do first, I'm going to do the easy one first and then do the multiplication at the end. But in either case, what am I going to get here? I'm going to get this multiplication first, so I'm going to copy this one down, multiplied by a new 2 by 2 matrix. So what am I going to get? I'm going to get 0, 0, 1, 0, 0, 0. Oh, sorry, I did that wrong. Careful. 0, 2, 0, 0. Now I want to do this matrix multiplication, which shouldn't be too bad because I gave myself one that had zeros in it. So what am I going to get here? I'm going to get 0, negative root 3 over 2 times 2, which cancels. And then here I'm going to get 1/2, 0. Here I'm going to get 0, 2 over 2 is 1. And here I'm going to get root 3 over 2, 0. So root 3 over 2. This is the standard matrix of doing these three things in the plane. Instead of trying to figure out what that would do and how I would move those points around, I just break it into 3 stages. I find the standard matrix of each one. Then I find the composition standard matrix by looking at matrix multiplication on the left always for these, because it's R pi over 3 following T2 following T1. Please subscribe right here and hit the notification bell there. I think now. I'll see you next time.